In this video, I want to talk about the relationship between conservative forces and potential energy functions. In particular, what I want to get to is that if you have a potential energy function, you can find the associated conservative force by taking the negative of the gradient of that potential energy function. All right, so we're going to do some examples with that later, but first I want to back up and talk about the relationship between work and potential energy. And we'll get to this relationship in just a moment. So, the general expression for work, basically if we've got a force that could be varying, could be in multiple directions, multiple directional components, along some infinitesimal displacement, which could also be changing, that's how you calculate the work. In principle, this is how you do it. Depending on the situation, the calculation could be very nasty due to the integration, due to the fact that this could be changing values and directions, and due to the fact that this could be changing directions. There are some simpler special cases. If you've got a varying force, say with a varying x component and a displacement only in the x direction, this is a relatively easy calculation, especially if this is a function of x. Another really simple special case is if you have a constant force that's not varying and a straight line displacement, could be in a different direction, work is just the dot product. This general expression for work combines all the different complications that could come into things, varying forces, varying directions, and so forth. Okay, great. So that's work. Now, there's a relationship between work and changes in potential energy. For example, if I move this pen upward, it has an increase in potential energy, gravitational potential energy, but the gravitational work is negative. Gravity's pointing downward, the displacement's upward in this case. It turns out the work done by gravity, not by me, but by gravity, is exactly the negative of the change of the potential energy. So that's a theorem you can take to the bank. So now we can put that together. We look, the work done by a conservative force would be this work expression, but just applied with a conservative force, and then we can relate that to the negative of the change of the potential energy. Great. What this means then is that there's a integral relationship between conservative forces and changes in potential energy. In other words, if you do an appropriate integral of a force over a displacement, you get something related to the negative of the change of the potential energy. Well, if you can integrate one way, you could take derivatives to go the other way. So in other words, to get potential energy changes from conservative forces, you integrate. If you want to get conservative forces from potential energy functions, you take a derivative. And remember, this is the gradient. It's basically a three-dimensional vector derivative. All right, so there are theorems of calculus that exactly relate this sort of thing to this sort of thing. If this is true, theorems of calculus say this is true, and vice versa. So I'm not going to go into that. We're just going to look at a couple of examples. And the reason I want to do this is this exact beautiful expression here can be nasty, but often this is much simpler. In general, taking derivatives is easier than taking integrals. Okay, so let's just do a couple of examples. So now first let's unpack the gradient of the potential energy function. Well, so the conservative force is the negative of the gradient of the potential energy function. The gradient of the potential energy function is this. So it's basically a bunch of partial derivatives and appropriate x, y, and z hat unit vectors. So, examples. Let's consider a spring. So a spring, an ideal spring, has a potential energy function proportional to the square of the displacement from equilibrium. Call that x. Great. So that's our potential energy function. Let's find the associated spring force, the associated conservative force exerted by the spring. Well, here we go. We just plug and chug with our gradient expression. So we've got our minus sign, and then these are just placeholders for the partial derivatives of the potential energy function with respect to x, y, and z respectively. Those are giving components in the x hat, y hat, and z hat directions. All right, so here we go. Partial derivative of this thing with respect to x, well, 2 will come down and we'll just have kx. Great. Partial derivative of this thing with respect to y, which would go here, well, there's no y's in there at all, so that's 0. Partial derivative of this thing with respect to z, another big fat 0. Because remember, when we take partial derivatives with respect to some variable, say y, everything else is held constant. So x is a constant when you're taking derivatives with respect to y. X is a constant when you're taking partial derivatives with respect to z. Great. So our result is that the spring force is minus kx. That's the amount in the x hat direction. Or if you wanted to say there'd be an x component of force of value minus kx, which of course you recall is the restoring force for an ideal spring. All right, let's do an even simpler example, gravity. We can have a gravitational potential energy function. This of course is the approximation near the surface of the Earth. Gravitational potential energy is mass times the magnitude of the acceleration due to gravity times y. For this, of course, we're taking y to be in the upward as the positive y direction. All right, so we'll write let's try and calculate the gravitational force from this potential energy function. Well, we've got to take the negative of the gradient of the potential energy function. So I've written out the gradient here. So now, mgy. Derivative of that with respect, I should say partial derivative of that with respect to x is 0. Partial derivative of this thing with respect to z is also 0. And then finally, partial derivative of this with respect to y is just mg. So we get for our result that the gravitational force is, we got this minus sign, we get minus mg, and then this direction y hat. Y hat points upward, so this gives a gravitational force of value mg in the negative y direction. Great, so that all checks out. So these are very simple examples, but this expression is general. Basically, this defines the relationship between conservative forces and their associated potential energy functions. And this really is just another way of writing this, utilizing vector calculus. All right, so hopefully you found this example useful. Will we utilize this relationship? It turns out that there's a similar relationship to this that exists between something known as the electric potential and the electric field. So we'll get to that in due course. Thank you.